So very first of all, we shall begin with the problem statement. The problem statement starts with a discrete time random process x of n is generated as follows. X of n is given to us, which is computed by summation k is equal to L to P over a of k into x of n minus k added to w of n, where w of n is nothing but a white noise process with the variance represented sigma suffix omega square here. Another process z of n is found by adding noise to x of n. Z of n is represented mathematically, here x of n added to v of n, where v of n is a white noise with the variance of sigma suffix v square that is uncorrelated with w of n here. The problem statement extends to, first of all, the part A to find the power spectrum of x of n, and in the part B to find the power spectrum of z of n. So this is our problem statement. So the two tasks are to be completed, and both of the tasks require to have determination of power spectrum of the random processes, first of all for the x of n and next to that for z of n. Both of the random processes as per the given problem statement have been mathematically represented with sufficient information. We get back to them. So here we have the first random process denoted by x of n. So as we find here, x of n is determined by having the two terms onto the RHS. First, the summation process for k is equal to L to P for a of k in multiplication to x of n minus k, and the second term is w of n, which is called a white noise process. So into our previous videos from the same chapter, the white noise we have learnt into the 15th topic. Here in this particular white noise process, there it is also mention of the variance denoted sigma suffix omega square, omega not, it should be a w here. So after this x of n, so x of n we shall be requiring to find the power spectrum into the task A, part A here. Another random process is there, z of n, that is derived by having x of n, the initial one from the previous equation, and v of n, which is a noise here. So v of n is again a white noise random process, and it is having the corresponding variance denoted sigma suffix v squared, and it is also mentioned that this white noise is totally uncorrelated with w of n. So this is the problem statement. So we first of all focus our attention to have solution of part A. So part A is finding the power spectrum of x of n and then finding the power spectrum of z of n. So for part A, as we have seen, x of n is the random process, and we can call it to be the output of an all pole filter driven by the white noise. To look at the expression represented here, this is our conclusion. So from this representation, it is very clear that x of n is nothing but the auto-regressive random process. The special type we have seen in our 20th topic for the same chapter here. So the abbreviation can be AR process. So as AR process is having q is equal to 0, the number of zeros, only the p's are there. So AR in bracket P is the abbreviated representation of the same random process. So that is our x of n. So for such a random process, thereupon in the 20th topic we have seen the power spectrum can be expressed by the mathematical formulation like this. So the required power spectrum we have represented onto the left hand side, p suffix x, where p is the power spectrum and for which particular random process, here it is, so it is mentioned into the suffix. So x of n, hence p suffix n, p suffix x as a function of e to the power j omega. So it is computed by taking a ratio of the variance sigma suffix w square divided by mod square of a as a function of e to the power j omega here. Now sigma suffix w square, this is the variance with respect to the w here that we all know here, that is white noise as mentioned in the problem statement. Now what is this capital A as a function of e to the power j omega? So it is also given in the form A as a function of e to the power j omega, nothing but 1 minus the summation k is equal to 1 to p A of k in multiplication 2, here we have e to the power minus j times k omega. So the first equation where the substitution can be made from the second one gives answer to the part A. We were asked to find the power spectrum of x of n, and here it is the outlined expression for power spectrum of the random process x of n as per the given problem statement. Now we shall move further for determination of solution to the part B. In part B we have been asked to find the power spectrum of the random process z of n. So z of n has been formed by the addition of v of n, another white noise random process, to the previous random process x of n here. So that can be represented by this mathematical equation from the given problem statement. Here we have the first random process x of n and another new random process v of n, white noise type, is added to it, hence the resultant random process is z of n here. Now from the first equation into the problem statement for the x of n, RHS is holding the two terms. The first term for the summation k is equal to 1 to p a of k into x of n minus k added to w of n. So looking at the relation of w of n to that of x of n, we conclude that x of n is having a linear combination of values of w of n. So therefore x of n can also be expressed into this mathematical form. So we write here x of n is equal to the summation k is equal to minus infinity to n, or h of k multiplied to w of n minus k here. In this representation, the new thing is for h of k. So this h of k is nothing but the unit sample response of the filter that has generated the random process x of n. So the background you can check into all the videos right from 19th topic to the 21st topic there. So autoregressive moving average process, autoregressive process and moving average individual processes we have been discussing so far with the help of those filter functions here. So now this is the AR process. Now along with this h of k, as we shall focus on to the second part here. So x of n we have expressed by this particular expression. Now it's time to focus on to v of n. So v of n is uncorrelated with the w of n, which is a part of x of n into the first equation of the given problem statement. So therefore v of n is uncorrelated with x of n also. So using the property of uncorrelatedness of the random processes in terms of the auto correlation sequences, we can have the further equation like this. So for the intended random process, that is z of n here, we write its autocorrelation sequence by r suffix z as a function of k. So it is nothing but the individual sum of the autocorrelation sequences of the random processes. So we have Rx of k, autocorrelation sequence of the random process x of n, added to Rv of k, autocorrelation sequence of the random process v of n. So from the autocorrelation sequences, we can also find out the power spectrum, as we know that the power spectrum is nothing but the Fourier transformation of the autocorrelation sequences. So from this equation we can also write for determination of the power spectrum or the power spectral density of the z of n random process, it is p suffix z as a function of e to the power j omega, the addition of power spectral densities of the random processes x of n and v of n. So for x of n random process, there it is p suffix x as a function of e to the power j omega that we have determined into the first part here, whereas p suffix v as a function of e to the power j omega is the power spectral density for v of n random process here. So here we move further for the power spectral density for z of n random process p suffix z as a function of e to the power j omega. It will be sigma suffix w square, the variance as represented into the first part here, divided by the mod square of a as a function of e to the power j omega added with sigma suffix v square. So that is the variance. So the second part we have taken from the given problem statement here. So because of the uncorrelatedness with the w of n, we have the variance as the required solution for the power spectral density of the corresponding random process. So here it is sigma suffix v square here. Now the substitution of a as a function of e to the power j omega can also be made from the 1 into the part a here. Further, we simplify this representation of the power spectral density for z of n. In the numerator, we express sigma suffix w square added to sigma suffix v square in multiplication of mod square of a as a function of e to the power j omega. This complete addition is divided by the mod square of a as a function of e to the power j omega. So this completes the solution of part B that it was required. So part B answer can be outlined this way here. So as there were two parts A and B, we were required to find the power spectrum or the power spectral densities of the random processes x of n and z of n. Both the answers we have successfully obtained here. So this concludes our problem number 1 for the random process.